Thanks, Paul, for the introduction and for allowing me to take up an hour of your time. Thanks to all of you for coming in sleepy postprandial hour to this talk. The first thing I should say is that everything I'm going to tell you about is going to work with Young and Gabriel Romangold. The second thing I should say is by way of a disclaimer, although there are things being harnessed by Homotopy behind the scenes in this talk, little to no of that is going to appear in the talk. If I have time, which I won't, at the end I will give you some indication of what's happening there. But
how you harnessed?
So what this talk is about is what you do once you have things harnessed by Homotopy. You ride them into the sunset of applications. So this is about the sunset of applications. One is a graph. And for me, what a graph is a finite one-dimensional CW complex. And I'd like to propose the following question, which is not a mathematical question, it's an intuitive question. How connected is my graph? So if we think that the graph represents some kind of network that connects nodes together by abstract relationships or flows of information or something, then it seems relevant to try to understand how good of a job the graph is doing connecting these things together. So if you have some notion of connectivity because you've seen some graph theory in the past, I want you to forget that. Let's go into this afresh. So what kind of graphs might I be thinking about? Here's a graph. That's the star graph, S3. Here's another graph. The lollipop graph, L. Here's another graph. That's the data graph. So if I want to understand how connected these graphs are, then one reasonable way to start is by starting to disconnect. So by that I mean, let's pick this vertex here because it's the only interesting one. It's the only essential vertex. So here's a piece of terminology that I'll use throughout. Essential means having valence greater than or equal to 3. So the essential vertices are what keep graphs from being manifolds, which are boring. So let's remove that essential vertex, and well, that's what we get. Okay, well, let's remove this essential vertex, and what happens when we do that? We get something that looks like that. And we can remove either one of these essential vertices, and the result will be the same. And all I want to point out about these pictures is that there are 3 components here, and there are 2 components here, and there's 1 component there. Okay. So somehow, by starting to disconnect the graph, we've already seen some difference in what we might think of as how connected they work. But there's another difference to be noticed, which is that, well, this process of removing essential vertices terminates here for these 2 graphs, but it doesn't terminate here. We can keep going. So let's remove the other one, and what happens then? We get 3 lines. Okay. So I want to define an invariant of graphs called delta sub gamma I. And what it is it records how you do this process. So it's the size of pi 0 of the complement of a set of vertices in gamma. And it's the largest such that you get by removing a set of I many essential vertices. W is the set of essential rows. And so we get some sequence of numbers associated to a graph, which in some way are one answer to this question of how connected the graph is. And I should say that I don't know exactly who invented these invariants. I learned about them from a paper of Eric Ramos. And it's possible that he invented them, but they seem quite natural, so I wouldn't be surprised if they've been around for longer. So just to do one example, gamma is the complete graph on 4 vertices, so here is that graph. Then we can sort of record I and delta I for this graph. If we don't remove any, then certainly the graph was already connected, so that's 1. If we remove 1, it remains connected, that's 1. If you remove any 2, you end up with 2 connected components. If you remove any 3, you end up with 4 connected components. If you remove all of them, you end up with 6 connected components. And for various reasons, it's good to say that if I remove more vertices than I actually have, then what I get is minus infinity. Okay.
Really?
Yes. Okay, so the main theorem of this talk is going to be about this invariant. How can you compute this invariant? In order to state that theorem, I need to introduce something that will seem very unrelated. So I'm going to write font k of gamma for the configuration space of k ordered points in gamma. So this is this space of k tuples with distinct points. In gamma, most of the time I'm going to care more about the unordered configuration space, which is the quotient. Of course, these definitions didn't use that gamma was a graph, but that's the example that I'm interested in. And often, indeed usually, it's good to consider all of these configuration spaces at the same time. And I'll call that space B of gamma, thought of as the graded space. Okay. So the theorem, main theorem, is that so if I'm working over a field, and if my graph is connected, and has one of these essential vertices, in other words, it's not a manifold, then the ith Betty number over F to say something, this is only an assertion about sufficiently large K. So, for large numbers of points in the graph, the ith Betty number of the K configuration space is computed by number of points. And the degree of that polynomial is exactly given by this ith connectivity invariant minus 1. That's the theorem that I would like to talk about.
Can you make little k effective?
I think so. We haven't yet, but I think we could do that. Any other questions?
Will the polynomial be explicit eventually, or?
Eventually in the history of the world, I hope so. Eventually in this talk, absolutely.
Okay, so it's just the existence of.
Just the existence, yeah. Just the existence and the degree. Couple of remarks. First remark is that saying that it was connected and had an essential vertex was only for ease of statement. This determines the growth for any graph. Growth. The second remark is that the case of a tree was proven by Eric Homos. And this was conjectured to be an upper bound on the degree by in the same paper. So we prove that conjecture and show that it's also a lower bound. You might ask, and it's a reasonable question, is there actually any difference at all between the case of a tree and the case of a general graph? And it turns out that there is a qualitative difference that makes the case of a general graph much more complicated. And assuming that I remember to, I'm going to comment on that later. If I don't, you should remind me.
Yeah, I was just wondering about this quotient map order to unordered configuration. So over points which have an essential vertex is probably not locally trivial.
That's right. It's not.
Is it a quasi-vibration or anything, or is it? So we have no homotopical control a priori.
Not in the kind of inductive sense that we are familiar with from manifolds. Yeah. So, the other thing I wanted to say is that I motivated this from the graph point of view, but I would like you to think that this theorem you could read either way. If you care about graphs, then this is saying that this graph invariant is computable in a topological, homological way. On the other hand, if you are someone like me, perverse enough to think that configuration spaces are intrinsically interesting, then this is saying that some limiting behavior of those spaces is determined by this combinatorial invariant of the background space.
So in particular, the dimension is given by this number of essential vertices.
That's right, yes. So that's something a little bit surprising. That relates to this convention that minus infinity is, so a polynomial of degree minus infinity is 0. And so this was something that was certainly known before, but it's maybe not, it's definitely not obvious that there is no homology at all above the number in degrees larger than the number of essential vertices of the graph. Yeah, thanks for that. Thanks for that comment. Okay, so let me just tell you a few things about configuration spaces of graphs, because they're not yet the most super well-known spaces, and not everyone's intuitions are all set up for them. So the first result that I'd like to mention, which explains part of the title, which is now erased, is a theorem of Christ corrected by Aaron Abrams, which says that this configuration space is always a k by 1. And goes those fundamental groups are called the graph braid groups. By analogy with the case of R2. And these are groups that are interesting to geometric group theorists, and at least I say that when there are any geometric group theorists in the room, I hope. Be careful. And to roboticists and people who study motion planning and things like that. So those are the graph braid groups. What kinds of spaces do we get?
What kind of pie do you get?
Yeah, exactly. What kind of pie do you get? So let me give you a few examples that tell you what kind of pie you get. So here's the simplest example that is not a manifold. This star graph S3. So I'd like to show you a non-trivial element in pi 1. Because maybe your intuition from one manifold is such that you would expect this to be trivial. Let's see what color. Yeah, let's just see maybe this color. Well, there's my graph, and I start out with a configuration of 2 points. I should have said that. K equals 2. And well, here's something you can do. You can take this point and move it to there, to the essential vertex. And then you can do something else. You can, having cleared this point out of that leg, you can now move this point into that leg. And then you can do this again. You can take this point and move it into that leg. And this describes a path in the configuration space from that configuration to the same configuration, because this is the unordered configuration space. In other words, it's a loop. So claim that the class of this path is non-zero. And in fact, the resulting map from S1 into the configuration space is a homotopy equivalence. So the configuration space 2 points in this 3 star is a circle. So that's one example. It might not be the most absolutely thrilling example of a group. Here are some other cool examples of groups that you get. So, further examples, I'm going to say the ordered thing, but I don't know, that differs by the unordered, from the unordered by sigma k, so not a big deal.
You're saying what? By?
I'm sorry?
You said it differs from the unordered by?
Sigma k.
But didn't you just say it's not a bundle? Projection? That was
Oh, I think I misunderstood your question. The projection from ordered to unordered is a bundle, no problem. The projection from configurations of k points to configurations of k minus 1 points is not a bundle. So we can't study them inductively that way, but absolutely, that's still the groups are just, one is an extension of the other by sigma. No big deal. Yeah, sorry if I misunderstood your question before.
But you know, if one point is an essential vertex, doesn't the neighborhood locally of the other configurations look different from if it weren't? That's, I don't quite see why that would be. Over the configurations which have 1 point on an essential vertex.
Maybe let's talk about it afterward. It's not going to. I'm never going to use the ordered configurations throughout the entire talk, except to give these examples.
No, if 1 point is the middle point in that configuration, then around that, the other points have 3 components, whereas if it were here, it has 2 components. So how would this be a bundle?
Yes, I think it's.
So is that the other question? So it's the other question. Okay. So I confused the 2 questions. question.
Yeah, I think that's you're saying exactly
Yeah,
why
that's-
complicated components
yeah.
one is not good. Okay, so the ordered configuration space of 2 points in, let me give myself a little bit more room. Ordered configuration space of 2 points in a complete graph on 5 vertices, so that's a graph that looks like this. Where these crossings in the middle aren't there, they're not vertices. It's a non-planar graph. This is actually homotopy equivalent to a surface of genus 6. If you look at the configuration space of 3 points in the data graph on 4 edges, so that's a graph that looks like that. And this is, yes, this is homotopy equivalent to a surface of genus 13. And if you consider the configuration space of 4 points in the complete bipartite graph K33, which is the graph that looks like this, then that is homotopy equivalent to a surface of genus 37. So those are some groups that you get. You're probably wondering why surfaces, what's going on. I don't have a good answer for that. Maybe somebody has a good answer for that, but I don't.
What techniques are used to prove these equivalents?
Yeah, there are, the techniques that I'm aware of are exhibit a subspace, which is a cell complex. That's a deformation retract, and count cells, and use some argument to see, well, you can get a local picture and see that it's a manifold, and then use some argument to see that it's orientable. This is really only in this case. I would have to check the references to see these, but they're also by appeal to some cellular, the same cell complex. In this case, once you've done taking care of the local picture and seen that it's orientable, then you can do an Euler characteristic count very easily and see that the genus has to be seen.
But is it in all cases one has to sort of guess an analog of this rotation map from the right to the left, or is this a systematic procedure to produce the right inside? What you're describing is people produce a map from the surfaces into the configurations, which probably is an analog of this. Pictures.
So
Can one guess the thing, or is this?
maybe what I'm about to say will answer your question, and maybe not, in which case you can ask again. The subcomplex, it's actually a cubical complex, is canonical and exists for any graph. And in at least this case, it's homeomorphic to this surface. I think probably it's homeomorphic to the surface in this case as well. I haven't checked that, and I'm not sure about the 57. But in any case, the cell complex is always there.
But it might not be a manifold.
I don't think there's any reason it has to be a manifold in general. In fact, it certainly will not always be a manifold. Any other questions? Okay. Maybe I'll just say that out loud. So, the things that I will say out loud while I'm erasing this board are 2 more results, which are about what kind of invariance of graphs you get from the configuration spaces. The first theorem says that the first homology of the second configuration space of the graph is torsion-free if and only if the graph is planar. So planarity is detected. The second theorem, that's a theorem of Cohen-Park. The second theorem says that the homotopy type of the configuration spaces of trees, in fact, the homotopy type of the configuration space with 4 points in a tree determines the tree up to homeomorphism. It's a theorem of Sabaka. And according to the theorem, which is now erased, the main theorem, the configuration spaces also remember connectivity information about the graph. So I think that the big question on my mind that the theorem in the talk is partially answered is what kinds of invariants do the configuration spaces know about the graph? Okay. So let's, well, on the way to talking about how to prove the theorem about the polynomial growth, let's first address a weaker question, which is why should the growth be polynomial at all? Forget the degree. Why is it polynomial at all? And I want to motivate that with something classical from the manifold case. So if I have a manifold with boundary, then I can cook up a map from this total configuration space to itself that raises the cardinality degree by 1. And I'm sure many of you have seen the picture I'm about to draw. The way it works is you have, say, 3 points over here in your manifold, and you send that to the configuration that has those same 3 points, or almost those same 3 points, together with a 4th point very, very far away. And that's why you need the boundary there. And the relevance of this map is theorem of Duff, which says that you can do map from homology of bk to homology of bk plus 1 isomorphism for k much bigger than I, and k much bigger than I can be made precise, and there's an entire industry devoted to making k much bigger than I more precise. But let me just say it like this for now. So this is kind of an or example of homologic stability. And you can wonder, well, what if I have a graph with boundary? Right? I have some dangling edge, and I can insert a particle near the end of that leaf. That's a perfectly good map, no problem. Homological stability always fails. As soon as the graph is not a manifold, no homological stability, no dice. But there's a reformulation of Milgras's theorem that will allow us to generalize. It says that, well, what is this kind of total homology equipped with this map? What's anything equipped with a map? It's a module over the polynomial ring of one generator. There's a useless sounding statement. Well,
it's a dimension issue, right? I mean, n has to be a dimension at least 2.
Oh yes, I'm sorry. That's absolutely right. So,
The graph fades.
yes. So, I should have said that M was connected, and the dimension is bigger than 1, and so the comment was that, well, we would have known already that it fails for graphs because it fails for one manifolds. So, and that's absolutely right. But it doesn't fail for the same reason. So, or I don't know, one reason that it fails for one manifolds is that it fails at the level of pi0. Pi0 explodes. As soon as the graph is connected, the configuration space is connected. So pi0 is not the problem anymore. Excuse me. As soon as the graph is connected, it has an essential vertex, and the configuration space is connected. Okay, so the reformulation is that the homology of this total configuration space is a finitely generated module over the polynomial ring that's generated by sigma star, graded module over this graded polynomial ring. Okay, so the kind of
Where's sigma stuff now?
yeah, sigma is the map that is now eclipsed. So
why is this? I don't quite see why this is a reformulation.
well, maybe let me be over a field. Let's just say be over a field for the moment. Then it's a theorem of Hilbert about graded modules over graded polynomial rings. That says that if you have a finitely generated graded module over a field adjoin, say, n many generators polynomial ring, then that has eventual polynomial growth degree less than or equal to n minus 1. In this case, n minus 1 is 0. So there you go.
The Noodle normalization.
I'm sorry?
Yeah, by some sort of Noodle normalization, right?
I'm sure that's correct. Okay. So the theorem that is, we would like to say, an analog of homological stability for configuration spaces of manifolds says that gamma is a graph with a set of edges called E. Then the homology of this total configuration space over the integers is a finite generated module over the polynomial ring generated by the edges. And by that same theorem of Hilbert,
So are these kind of the three edges, the ends, or all edges?
no, all edges. I'm
How do you insert something in the
Indeed. So by that same theorem of Hilbert, this implies the eventual polynomiality of degree at most number of edges minus 1, which is bad bound. We would like to do better than that. Okay, so to address Stefan's question, if I want to have a polynomial ring generated by the edges x, then I have to find some way to add a new point to an edge. If it's a dangling edge, that's no problem. We know how to do that. But if it's an internal edge, then think about it, it might be a little hard to see how to do that continuously. Where are you going to put it? So where does the module structure come from? So this goes under the name of edge stabilization. What is edge stabilization? If I'm given an edge, then I'm going to give you a map called stabilization of that edge. It's also going to increase this cardinality gradient by 1 from the configuration space to itself. And these maps are going to commute, therefore, the module structure. Okay, so how does this map work? Here's the edge. Here's a zoomed in picture of the edge, meaning that there's lots of graph that happens outside of the edge, but we don't care. The edge is parametrized, and it has a sub-configuration on it. Maybe the sub-configuration looks like those three things. So this is a picture of my configuration intersected my edge, which looks like maybe some points x1 through xi ordered in the natural orientation of the edge, natural in the sense that I've chosen a parameterization, and so now there's You might also call it the unnatural ordering. So what am I going to do? I'm just going to do nothing to the subconfiguration outside of this local picture, and then I'm going to do something to this subconfiguration, and that will be the map. So what do I do to this subconfiguration? I send this subconfiguration to the collection of averages of consecutive pairs of particles or endpoints. So what does that mean? I take the first point and the endpoint and I average them.